All right, so now let's continue our discussion of using chemical reactions, balanced chemical equations quantitatively by talking about yield. Um, so up until now, when we've been using our stoichiometry to calculate the amount of product that's formed in a reaction, that's what we would call the theoretical yield, the calculated amount. All right, so if we just go back to the very first example, kind of the simplest example that we did, this idea of I start out with 5.25 moles of ammonia, how much urea, how much of my product will be produced, right? So this was the urea, this is the ammonia. And what we did in this calculation was said, okay, if all 5.25 moles of ammonia is consumed, then we would get this much urea. We would get 2.63 moles of urea. That's the theoretical yield of this reaction. If 100% of your ammonia is converted to urea, this is what your yield would be, okay? So that's what we would call the theoretical yield, the one that we calculate. However, anytime you're doing a chemical reaction in the lab, you're never going to get 100% of your yield. There's always a little bit that's a product that's lost, maybe on the side of a beaker or something like that, as well as the fact that chemical reactions aren't always 100% efficient. So we have our theoretical yield, which is what we calculate, and we compare this to the actual yield that we get at the end of an experiment. This is what we measure in the lab using our balance, for example. Right? So again, theoretical yield is calculated, and the actual yield is something that would be measured in the lab. Okay. Chemists often quantify like the success or the efficiency of a reaction by calculating the percent yield, which is where you take the actual yield, divide it by that theoretical yield, and multiply it by 100 to turn it into a percent. Okay, so a reaction, if it's perfect, you'd have a 100% yield. But of course, that doesn't really happen. You're always going to lose something. And so you typically will have something less than 100. Okay. Importantly is though, again, how to calculate that. So remember the difference between the actual yield and the theoretical yield. The actual yield is measured. And since we're doing pencil and paper chemistry for the lecture component of the course, that basically means you have to be told it in the problem, right? So the problem would say something like, this is how much product you actually got, calculate the percent yield. And so you would have to take that actual yield that's given and then compare it to the theoretical yield that you calculate using stoichiometry. Okay, so let's do some example problems. So we have phosphorus pentachloride will decompose into phosphorus trichloride and chlorine gas using this balanced chemical equation. Determine the percent yield if 3.45 grams of phosphorus pentachloride decompose to yield 2.10 grams of phosphorus trichloride. Okay, so our actual amount that we got at the end of the experiment is this. This is our actual yield, the 2.1 grams of phosphorus trichloride. In order to get the theoretical yield, I have to use my stoichiometry, right? So this is going to be using the balanced chemical equation here. So first of all, I'm going to start with what's given, the 3.45 grams of phosphorus pentachloride. And I need to get to grams of phosphorus trichloride. So remember, we have the same sort of strategy over and over and over again that we're seeing, and that is we need to use our balanced chemical equation. So we need to get to moles. What I like to tell students, because sometimes it can be confusing, when do you use molar mass, when not, do you use solution concentration, et cetera, et cetera. When in doubt, get to moles, okay? So in order to use your balanced chemical equation, you have to be in terms of moles of your reactants and products. So our first step is to get from grams to moles. And to do that, we'll need the molar mass. All right, so again, I'll just tell you the molar mass so we can go quickly. This is something you want to be able to calculate using the periodic table. 208.237261 grams per mole. And we'll also need it for the other for our product, the phosphorus trichloride. All right, and I know it's a lot of writing, but I'm getting in the habit of putting all my digits. I'm not rounding anything off because then I would incur some rounding errors. So I know it's a pain in the butt, but get in the habit of including all of your digits. Okay, and remember, we're going to convert this piece of information here into an actual conversion factor that we can use in our stoichiometry. And I'm going to have to put grams on the bottom. So 208.237261 grams. And I'm being good and labeling what I'm talking about because that will also help me keep track of units. Okay, so now I can use my balanced chemical equation to jump from phosphorus pentachloride to phosphorus trichloride, where I have 1 mole of PCl5 and 1 mole of PCl3. And again, I knew which way to put this because it's all about making sure your units cancel out at the end. Okay, if we were given the actual amounts in moles, we wouldn't have to do this next step. But since we're given the actual amount in grams, we're going to have one additional step, which is to get the grams of phosphorus trichloride. So 1 mole PCl3 is 137 grams PCl3. Okay. All right, and so again, just to with this, we've kind of been playing this game over and over and over again, but I want to emphasize this, right? I've converted this molar mass information, that's this term here, that allows me to jump from grams of phosphorus pentachloride to moles of phosphorus pentachloride. I then used my balanced chemical equation. That's how I got this mole ratio here. That's how I went from moles phosphorus pentachloride to moles phosphorus trichloride. And then lastly, use this molar mass for phosphorus trichloride to get back into grams, from moles phosphorus trichloride to grams phosphorus trichloride. Okay. So, all right, let me get rid of these colors just because they're going to be distracting. Next step is I lined it all up, right? And I knew how to line it all up because my units are going to cancel. So now I punch it into the calculator and get 2.27526 gram. Oh, okay. So punched it into my calculator. This is what I got. Now I'm going to go back and look at units, cancel the grams of phosphorus pentachloride, cancel moles of phosphorus pentachloride, moles of phosphorus trichloride, and I'm left with grams phosphorus trichloride, which is what I want. Okay, so that's my my theoretical yield. And again, I got that from calculations, right? That's how we get our theoretical yield. Calculating that if 3.45 grams of phosphorus pentachloride was consumed, if all of that was consumed, I would get 2.27 grams of the phosphorus trichloride. Okay, so last step always, because we're chemists, is Sig Figs. I have 3 Sig Figs at my starting number. I took all my digits for my molar masses, so I don't have a problem there. And then mole ratios are exact, so I'm not going to consider that. And I'm going to mark that. Okay. So if I was to be asked what the theoretical yield was, I would say 2.28 grams of phosphorus trichloride. All right, this is the theoretical yield. Now, when I go to calculate percent yield, I'm going to take that actual amount. So let me actually sort of move this up. All right, so percent yield is actual divided by theoretical times 100. The actual yield is what was given to me. That's that 2.10 grams PCl3. My theoretical yield is what I calculated, but remember, I'm not going to take the rounded value. I'm going to use this unrounded value, this one here, with all those digits. And I'm just going to keep my sig fig marked so I know how many sig figs my answer should have. But remember, we never do calculations with rounded numbers. So I punch this into the calculator, multiply it by 100, and I would get a percent yield of 2969%. Notice that actually these units of grams of phosphorus pentachloride have canceled out. And so I'm left with a unitless quantity, which is a percent, okay? And then I have to pay attention to sig figs. I have 3 in this measurement here and 3 in my measure or my theoretical yield. So I would round it to 3 sig figs. So this would be 92.3%. That's my percent yield for this reaction, which is pretty high. 92 is a great amount. Okay. So that's what so basically now we're just tacking on an extra step to our stoichiometry for reactions that we learned about in the previous 2 lectures. All right, so let's take a look at this problem here and see if we can't figure out what's a little bit different about it. So aspirin, so aspirin, which is acetylsalicylic acid, it's the most commonly used pain reliever in the world. You can get it by reacting salicylic acid. So let's make sure we're keeping track of who's who. This is salicylic acid, C7H6O3, with acetic anhydride, that's that C4H6O3, and this is what will give you aspirin, C9H8O4. This is kind of this big, ugly chemical equation here. This is actually a pretty simple reaction that you would learn about in an organic chemistry course, but it's a little beyond us to be looking at the structures of these organic molecules. So for now, we're just going to follow these chemical formulas here and trust the problem. Okay, so I'm gonna use my colors to sort of make sure we're keeping track of who's who here. So now we did a synthesis of aspirin where we used 104.8 grams of salicylic acid and 102.3 grams of acetic anhydride. Calculate the percent yield if the reaction gave 105.6 grams of aspirin. Okay, so this is our actual yield. Now we need to calculate the theoretical. And I can already tell I'm going to run out of space, so I'm going to copy. Okay, let me move this over to a new page so I have enough space to do this. Okay. So now let's calculate the theoretical yield. This problem's a little bit different in that I'm given some starting amount of the salicylic acid. That's the 104.8 grams. And I'm also given a starting amount of the 102 of the acetic anhydride, 102.3 grams. So what would be my theoretical yield? Well, now this is a lot like a limiting reactant problem. Okay, so first when I'm given the amount of both reactants, I got to figure out first which one's the limiting reactant. That will tell me how much of my aspirin is actually produced here. Okay. And we're going to need a little bit of additional information because we're going to start out. So we're going to pick one. Let's start out with the 104.8 grams of salicylic. I'm actually going to just abbreviate this for the sake of not writing 100 things. Salicylic acid we'll abbreviate as SAL. And what am I going to have to do before I can use my balanced chemical equation? Same thing we had to do, same game we play a lot here, and that's use the molar mass in order to get to moles. So again, I'll tell you what these are, but you should be able to calculate it based on the formula and using the periodic table. But in the interest of time, let's just put down all these molar masses. Molar mass of acetic anhydride, we'll call that AA. And lastly, we're going to need the molar mass of aspirin. I don't really leave myself enough room here. Aspirin, 180. Okay, so those are my three compounds. The salicylic acid I'm calling Sal, the acetic, and actually I'll just use my color coding. Salicylic acid I'm calling Sal, the acetic anhydride I'm calling AA, and the aspirin is ASP. Okay, so now I got to go from grams to moles. Again, when in doubt, go to moles. So I'm going to use the 138 point. Will take me to 1 mole of salicylic acid. Now I'm going to use my balanced chemical equation to jump from the amount of salicylic acid to the amount of aspirin, how much product is generated. So we have a 1-to-1 ratio. And then I'm going to have to compare it to my actual yield, which is in grams. So I'm going to need to make one more jump to get to grams of aspirin. Okay, punch that into the calculator. And if all of my salicylic acid is consumed, then I would get 136. Oops. All right, so that's what my calculator is going to spit out. I go and pay attention to units. Grams of salicylic acid cancel, moles of salicylic acid cancel, moles of aspirin cancel, and I'm left with grams of aspirin, which is what I want. So that's the theoretical yield starting with the amount of salicylic acid. But remember, this is going to be this two-step sort of thing where I have to first figure out what my limiting reactant is. So now I have to do a parallel calculation, basically the exact same thing again, but starting with the acetic anhydride. So now 102.3 grams of acetic anhydride. And I'm going to play the same game. First convert it to moles using the molar mass. Then I'm going to use my balanced chemical equation to take me from moles of acetic anhydride to moles of aspirin. Oops. And in order to compare these, I need to use the molar mass of aspirin to convert from grams to moles, or from moles to grams, rather. Okay, punch this into my calculator. Make sure my units cancel out. Make sure I set it up correctly. Everything cancels out nicely, and I'm left with grams of aspirin. Okay, so then how much is my actual yield for this reaction, or rather, how much is my theoretical yield for this reaction? Remember, we're going to look at our end quantities here and we have to compare them. And whichever one is smaller, that's the theoretical yield for your reaction, okay? I have enough acetic anhydride to make 180 grams of aspirin, but I don't have enough salicylic acid. I only have enough salicylic acid to make 136 grams. All right, one thing that I didn't do, but we want to make sure to do is always is Sig Figs. We have 4 Sig Figs in our starting values. We used a bunch of digits in our molar mass, so we don't have to worry about that. And our mole ratios are exact, so they're not going to limit as well. So we should have 4 in our final answer as well. All right, so that means that our theoretical yield is the 136.7 grams of aspirin. That's my theoretical yield. But then when I calculate my percent yield, I'm going to take that actual, the 105.6 grams of aspirin, and I'm going to divide it by the theoretical yield. But again, I'm going to take all those digits. I'm not going to encounter any sort of a rounding error. So I'm going to take all those digits. I'm just going to keep my Sig Fig marked so I know how many should be in my answer. Oh, I got to multiply by 100 too. Okay, so then I would punch this into my calculator and I would see that my yield for this particular reaction was 77.2519%. Right? I canceled my units out, so I just have a percent sign. And then going back and paying attention to Sig Figs, I should have 4. So this would be a percent yield of 77.25%. That's the final answer for this particular problem. Okay.